All right, guys, Mr. Antonucci here, and we're going to continue on with our instruction about using the log rule for integration. And what happens from time to time is integrals involve rational functions where they are in what's called an improper form. And that's where the numerator degree is greater than or equal to that of the denominator. And long division might end up resulting in a form in which you can apply this log rule. So here's an example here where we have an improper rational expression where the numerator's degree, x squared, is equal to the denominator. So we're going to use long division here, and I'll show you, remind you how to do this. So you have x squared plus x plus 1, and we're going to divide that by x squared plus 1. So we got to think x squared times what gives us x squared? Well, just 1. So you put a 1 above the 1 column, and then you multiply 1 times the x squared plus 1, and you get x squared plus 1. Then you subtract just like we did in old school long division, and you get 0, and then you bring down anything that's left over, and you just have x. Okay. X has a lower degree than what you're trying to divide by. So this is your remainder. And you write that, since it's positive, as plus 1 over whatever the divisor was. In this case, it was x squared plus 1. So our integral becomes 1 plus 1 over x squared plus 1 dx. And the antiderivative of 1 is x. And um, the oops, I forgot the x here. That should have been an x, which makes this an x. So this is u prime over u in this form right here. The u would be x squared plus 1, which we can multiply by a half to get that to work out. So you'd have 1/2 natural log absolute value of x squared plus 1. Now the absolute values are unnecessary here because x squared plus 1 is always positive. Don't forget your plus c, and you have your answer. Now, you can always check these by differentiating. And if you took the derivative, you would get back to this step here. And then if you added those terms, you would get back to this step right here. So this next example we're going to look for, or excuse me, look at, gives us another example where the log rule is kind of disguised in a sense. So let's go through it to help you recognize how this one should work. So we have x squared plus 1 quantity squared in the denominator and 2x in the numerator. Now, some people might think, don't write this down if you're taking notes, but you might think, well, let's FOIL out the denominator, x squared plus 2x plus 1. And then the u would be x squared plus 2x plus 1. du is 2x plus 2. Now the 2x is there, but we can't adjust for the plus 2 um, for this one. Okay, you can only multiply or divide to adjust for constants. So this is not the route we want to go. What we do want to do, however, is let u equal x plus 1. Okay, if u is x plus 1, then x is u minus 1. You just solve that equation for x. And in either case, du equals dx. So the integral becomes the integral of 2 times u minus 1, 2 times x, over u squared du. Now, the nice thing about this is you can factor that 2 out and split apart the subtraction into u over u squared minus 1 over u squared. And then this is going to be 2 times the integral of 1 over u minus, now I can't simplify this, but I can, in order to use the power rule, rewrite it as u to the negative 2 du. All right. So this is going to be 2 times the integral of 1 over u, which is natural log absolute value of u. And then the u to the negative 2, using the power rule, you add 1 to the exponent, so it's negative 1, multiplied by the reciprocal, which is negative 1. But since it's being subtracted, it turns this to addition. Okay, plus c. So now what we're going to do is I'm going to distribute the 2 and back substitute what u was. So this would be 2 natural log absolute value of x plus 1 plus 2 over u, which is x plus 1. I'm going to rewrite this -1 exponent. I'm going to drop that whole thing expression to the denominator, plus c. Okay? All right. Again, you can check the result by differentiating. All right. So those methods involve rewriting a disguised integrand so that it fits one or more of the basic integration formulas. And so here is, oops, didn't mean to put a big long line on there. Here are some guidelines for integration. You want to learn a basic list of integration formulas. You can easily find those usually at the beginning or the end of a book. Find the integration formula that resembles all or part of the integrand. And sometimes you have to use trial and error. You find a choice of u and make the integral conform to that. When you can't find unit substitution that does work, try altering the integrand. You might try a trigonometric identity, multiplication and division of the same quantity, different things. Sometimes you have to be a little bit creative. If you can find antiderivatives symbolically using technology, I advise against doing that regularly, but you can use that to help you check to see if your answer was right. And then you can always check your answer by differentiating. So here's another one. We want to use u substitution and the log rule by solving this differential equation. Because the integrand is a quotient whose denominator is raised to the first power, we could try the log rule. So what I'm saying is y is equal to the integral of 1 over x natural log of x dx. If you notice, in here is a 1 over x, which is the derivative of natural log. So if we pick our u to be the natural log, then du is 1 over x dx. It might be helpful if I rewrite the integrand as 1 over x times 1 over natural log x dx. Okay? Or you can think of this as 1 over x divided by natural log x dx. In either case, you would end up with du over u. Okay? Or, if you had it written the other way, it would be 1 over u times du. In either case, the antiderivative is going to be natural log absolute value of u plus c. And back substituting the u, you get natural log of the natural log of x plus c. So you have a log of a log, a log inside a log there. Okay? All right, guys. Well, that's it for this section. Hope that was helpful to you. As always, reach out if you have any questions. Take care.